Guys, this is where I left you. We did a couple of structures and some examples of Lewis dot structures of HCl, H2O, and NH3. And I told you there's more examples to come because you've got to get really familiar and comfortable with this topic, because some of the organic chemistry stuff that we're going to be learning this semester is going to build upon this. So I want to do another example, and this time I want to do CH4. Now, CH4, carbon's a nonmetal, hydrogen's nonmetal, all nonmetals across the board, so therefore this thing is covalent. And that covalent structure is going to have a total valence count, just like we've done all of the other times. All right, so carbon has 4 valence, because that's in group 4A. And hydrogen has 1 valence, because he's in group 1. Well, there's 4 of them in total, so that gives me a total of 4, and then I add them all together. So 4 from carbon and a total of 4 from hydrogen gives me a grand total of 8. Well, once again, I told you don't feel comfortable with the 8 number because it's going to quickly change. We also tried to figure out the center atom, and the center atom can never be hydrogen, so my only choice here is carbon, so there we go. And then there's 4 hydrogens that go around this carbon. All right, so I told you just kind of write them around the center one, kind of make them even, and we'll figure all of the structural stuff out a little bit later on down the road. So you would put carbon in the center, and you would draw 4 hydrogens around it. The next rule, or the next step, says connect everything to the center. So that means each one of these hydrogens have to be connected to the carbon in the center. So there you go. And when you do that, each line takes away 2, because each line is a bond, and that bond represents 2 electrons. So I count them up. I've got 2 from the left, 2 on top, 2 on the right, and 2 on the bottom. That's 2, 4, 6, 8. And we appreciate, because there's nothing left. There's no free dots that I can put anywhere. There's no extra electrons that I have to worry about. This took away all of the 8 that I am allowed to assign this structure. Well, now we've got to go back and we have to make sure that all of these are happy. Well, when I do that, hydrogen, we said, caps at 2. So the top one, the right one, the bottom one, and the left one, they all have 2. Because they have that bond that's attached to them. So all of the hydrogens check out, every single one of them, and I'll just put a check mark beside of each one. The carbon is like a traditional atom. It wants to fulfill the octet. So 8 is its magic number. And folks, it gets 2 from every line. So if you go around and count 2 for each line that's drawn to it, it's 2, 4, 6, 8. Just like we started with. So this structure at this point is a very happy structure. It is very happy with the way that you've structured it. It is very stable. It's a very common organic molecule. And this is something that we are going to start calling methane. methane. So a little bit later on down the road, in another lecture module, we're going to start talking about organic molecules, and methane is going to be a fundamental building block for us at that time. And you've just drawn the structure of it using the rules that we've talked about with Lewis dot. Okay, so now let's do another version. Let's go in and do CCl4. This is called carbon tetrachloride. This one's going to be a little bit different. So carbon is in group 4, therefore 4 valence. Chlorine, if you go to the periodic chart, you're going to see that's in group 7. Up at the very top, you'll see 7A. Well, there's 4 of these in total, folks. 7 times 4 is 28. 28 plus 4, you're going to have a total of 32. Remember, I told you don't get comfortable with the 8 value. And here's our example, the first example, where it doesn't add up to 8. But you know what? It's okay. Our rules do not change. So we go through and we try to figure out, well, which one goes in the center? Is it carbon or is it chlorine? We've got to figure this one out. Okay, well, here's the shortcut method. The shortcut method is going to tell you that if you have more than one of them, it's probably not going to go in the center. Now, who knows in the world of organic? It could rearrange, and it could, but if I was going to take a first stab and try to bet money on it, if I have multiple ones, as in the case of chlorine, that probably will not go into the center of the structure. So this leaves me with carbon. The other way that you can determine this is looking at the atomic number. Very often, the one with the lowest atomic number will go in the center. So whichever one has a lower atomic number, that's the one that you go with. If you look at carbon and you look at chlorine and you look at their atomic numbers, remember that's the value that represents protons and electrons, okay? Carbon will have a lower atomic number. Therefore, carbon goes in the center. So either one of those rules will basically work for you, if I'm going to be honest with you, almost every single time throughout this class. So I'm going to put carbon in the center, and I'll put the 4 chlorines all the way around it. I'll try to make it symmetrical and even, just like I did up above. And now I'm going to go through and connect everything to the center. A line there, a line there, a line here, and a line there. I count them up. 2, 4, 6, 8. So that takes away 8 from my 32. All right, so I'm going to take 32 minus 8. And what do we get? Do the math. That's right, 24. So I've got 24 dots here that I'm going to have to spread evenly around the molecule. And I do it evenly most of the time in the beginning. All right, and I do them in pairs. I know that doesn't sound normal because we said electrons don't show up in pairs, but normally if you do them in pairs, it works out in Lewis dot structures. Trust me, I've been doing this for a while, okay? Just go with it. So there's 2, and then there's 4, and there's 6, and there's 8, and I now go around another cycle. So there's 10, and there's 12, there's 14, there's 16, there's 18, 20, 22, and 24. So this is where I have to stop. I don't have any more dots that I can assign. I only had 24, and I just assigned 24. And now I back up. I look at my structure, and I figure out if everyone has the octet. Well, I start with my chlorine first. So you count each dot once, and the line represents 2. So 2, 4, 6, and 2 from the bond is 8. Well, if that chlorine works out, then this one will work out. It's got 2, 4, 6, 8. This chlorine will work out 2, 4, 6, 8. And this chlorine works out 2, 4, 6, 8. All of those happy. And now the only thing left is my carbon in the center. I want to make sure that it has 8 as well. And if I look at the lines, there's 4 of them. Each one represents 2. So 2, 4, 6, 8. And that fulfills the octet as well. Folks, there's the Lewis dot structure for carbon tetrachloride. That is also an organic molecule. It's covalent, it's carbon-based, and there's chlorine with it, but not a big deal. We said carbon can bring some buddies to the party, and in this case, he bought a set of quadruplets, and those were 4 chlorine atoms that he carried with him to the pitcher. So here's your example of doing one that doesn't quite meet 8 in total. We had a total of 32 here, but our job wasn't any more difficult at all, okay? Now, let's talk about another different type of structure. Let's look at CO2. Some of you will look at this molecule and automatically know that it's covalent. It's all nonmetals. It's carbon-based. There's carbon there with some oxygens. No big deal. So I do what I've always done, carbon and oxygen. Carbon's got 4, oxygen has 2, but there's 2 or 6 of them, but there's 2 of them. So this is a total of 12. So 12 and 4 is going to give me a total of 16. So I go back to the drawing board and I say, all right, what goes in the center? I look at carbon, I look at oxygen. Remember, I said the trick is most of the time if it shows up more than once, it's not going to go in the center. But if you're ever unsure, look at atomic numbers. The lowest one goes in the center. And carbon has a lower atomic number than oxygen does. Again, that's the value at the top of the periodic table in that element block. So carbon goes in the center, and I'm going to put oxygens around them. Okay, so if I look at these oxygens, I have to connect everything to the center, so there we go. And when I do that, that took away 4. All right, so I've got 12 that's left. 12 dots, that's the only thing that I can assign. I've always told you to start on the outside and do it evenly, okay? Worry about the center one last. But start on the outside, work around even, and you'll end up getting the correct Lewis structure. So I've got 12 dots, so I'm going to put 1, 2, and then over here, 3, 4. And then up here, 5, 6, and then 7, 8. And then down here, 9, 10, and then 11 and 12. And I have to stop there. I can't assign any more. I've already taken away the 12. I've got no more free ones that I can just put onto the molecule. This is it. So now our last step is to go back, and our last step is to double check to make sure they have octet. All right, so I look at this oxygen. 2 on the top, 2 on the left, 2 on the bottom, 2 from the bond, 2, 4, 6, 8. That one's good to go. If I look on the right-hand side, I do that oxygen the same way. 2 on top, 2 on the right, 2 on the bottom, 2 from the bond, 2, 4, 6, 8. This one's good to go. And now I'll look at the one on the center. If I look at the center one, I've got 2 from the left and 2 from the right, and that's it. Well, that's just 4. So we have an issue. Here's our first Lewis dot structure that doesn't go according to plan. But it's okay. There's a very easy way to fix this questionable carbon and give it what it needs as far as an octet goes. So here's the trick, folks. Listen up. The way that you fix this, if the center carbon is shy of the 8, you target one of the ones that are attached to that center, and you erase 2 of the dots. I just chose the left. You could have chosen the right. And I chose to erase the 2 on the side. Well, you could have erased the 2 on the top or the 2 on the bottom. It doesn't really matter. Just erase 2 of them. And then in its place, draw another line that goes there. Because remember, that line represents 2 electrons. You erased 2 dots and you drew a line, but that still represents 2 electrons. So if you count oxygen, you have 2 on the top and 2 on the bottom. That's 4. And then 2 from the first line. That's 6. And then 2 more from the bottom line. That's 8. So this oxygen's still happy. It still has the octet. You did not change that at all. The only thing that you did is convert 2 dots over to a bond. That was it. Well, if we look at this carbon's still not happy. This carbon has 2 from the top line, 2 more from the bottom line, and 2 from the right-hand side. That's a total of 6. He needs 8. So we're still 2 shy. So some of you might want to erase 2 more dots over here to the left and draw a 3rd line over here. But remember, I said I like symmetry. So do molecules. They like symmetry as well. So because we've already done the first one on the left, let's go back and erase 2 more dots over here. And now let's draw another line in between them. And this hopefully will give some symmetry to the molecule, and hopefully everything works out the way it's supposed to at this point. And if I double check the octet, 2, 4, 6, and 8 for the oxygen on the left. On the right-hand side, 2 on top, 2 on bottom, 2 from the top line, 2 from the bottom line. That's a total of 8 for the oxygen on the right. And now the carbon. The carbon in the center, 2 from here, 2 from there, 2 from here, and 2 from there. That gives me 2, 4, 6, 8. So there is your Lewis dot structure for carbon dioxide, CO2. It has what we call a double bond on the left and a double bond on the right. But this is its shape. This is its structure. All right, now I'm going to go back and pull in the methane that we did, CH4, and I'm going to go back and pull in the carbon tetrachloride that we did. All right, so I'm going to draw the dots all the way around those because there was something that we forgot to do. And I'm going to do all three of them at once. And that's assign the shape, folks. We've got to assign the shapes here. So let's do the shape of CH4 first. If I look at this shape, there are 4 things attached to the center and no free pairs on the center. Okay, so I'm going to go to this chart. I'm going to clean this up a little bit. And I'm going to look for 4 and 0. So bonded atoms to the center, 4 of them. So I scroll down and I find that there. And then the next column is number of lone pairs, and that says 0. So that is the setup that we need. And that molecular shape, according to Vesper theory, is tetrahedral. Again, think of a tripod, this time with an actual camera that's sitting on top of it. So CH4 is a tetrahedral molecule. If I look at CCl4, well, I've got 4 things attached to the center, and I've got 0 pairs of electrons on the center. I don't care how many free pairs are on the outside. That's not what that column wants. That column wants lone pairs on the center. Forget about everything else. So yet again, this structure is going to give me 4 things attached with 0 pairs. And it should say 4, 0. And that 4, 0 is the same as CH4. This is a tetrahedral molecule all over again. So tetrahedral is going to go there. Now I'll take a look at my CO2 up above. The CO2 has 2 atoms that are attached to the center carbon. It's not counting the number of bonds, it's counting the number of atoms. So 2 atoms are attached, and there's 0 pairs of dots on the center. So 2 and 0 is what we're going to be looking for. So on the chart, I find 2. Right beside of that, I see 0. That is the setup that I want. It's right here. And therefore, that shape, as probably expected just by looking at it, is a linear molecule. So this shape is linear. Folks, this is how we use Vesper. This is how we use Lewis dot structures in order to kind of get an idea of what these things are going to be like in a 3-dimensional world, because that's exactly what they are in. It is 3 dimensions. We get so used to writing things on a sheet of paper that we forget about that sometimes. But these molecules are actually molecules that exist, that you see, that take up space in a 3-dimensional form. They have shape, they have sizes, and all of this is very important in organic. Now, I've got one more example. Oh, before I go forward, polarity here. This CH4, this is a nonpolar molecule. Notice that I don't really have free dots anywhere at all, and because of that, this thing is nonpolar. There is not an unequal sharing of electrons because there's no electrons to actually put on there to share. So no dots that we have to worry about, therefore nonpolar. If we look at tetrahedral carbon tetrachloride structure, well, this one, you would say, well, wait a minute here. We have unequal sharing. So this arrow points up to that carbon. This arrow points to the left for that chlorine. This one points down for that chlorine. And this one points right-handed from that carbon to that chlorine. And they cancel each other out, actually. So the individual bond between carbon to chloride is polar. However, they have a net 0. The reason is, think of this carbon as a barrel, and there's a horse that's pulling against that barrel, and they're pulling at the same force. That barrel's not going to go anywhere, is it? The one to the top is going to cancel the one to the bottom. The one to the left is going to cancel the one to the right. So therefore, the net movement is 0. So the net dipole that's here, that's according to the compound. This is a nonpolar structure. There is polarity on the bond, but those bonds cancel each other out. And because of that, the net dipole is 0. They all just get canceled. Up at the top, the same reasoning goes there. This is a linear molecule. Is the bond polar? The answer is yes. I see some free dots here to the left, and I can draw that polarity, point it toward that way. And then over here on this side, I can draw the polarity pointed that way as well. Well, the one to the left is going to get pulled. The one to the right is going to get pulled. And if this was a barrel, again, in the center, and those horses were pulling in opposite directions, that barrel is not going to go anywhere. So the net dipole here is 0. That means that this also is a non-polar compound. It does not dissolve in water. Okay? That's really what this is going to boil down to a little bit later on. So, we're not done with Lewis dot structures yet, but hopefully you're becoming more familiar with them. And I hope what's happening is that you're looking back at your general chemistry class and you're thinking, you know, this is maybe something that I didn't quite get back in the day, but, you know, this doesn't seem very hard now this time around. And if you are telling yourself that, then excellent news for you. You're learning, and that's the purpose of taking this class. I want you to learn. I want you to understand that this stuff is not difficult, especially if you've had other people in the past and you thought, oh my goodness, how am I going to get through this lecture because I'm really going to mess up this test. I'm going to mess up these quizzes. I have no clue how to draw Lewis dot structures. What is all this mess? If you found yourself in that position, and now you're finding yourself in a position where you're like, wait a minute, this isn't hard. Why wasn't this explained this way the first time? Then you're making progress. And that's what this class is about. So in the next video, I'm going to do probably just one more example just to show you some differences here. And that example is going to come from an ion. I'm going to show you how to handle a ion whenever you get one. We did it with electron configuration. We did it in some of the other examples that we have talked about so far. So we'll do it again in Lewis structures as well. So in the next video, that's where we'll pick up. So be ready for me. Have that pen warmed up. Have that notebook paper clean because we're coming back.